Hi children, welcome to part 1 of class plus 2 physics first chapter electric charges and fields. In this video, I'm gonna discuss about Coulomb's law and its vector representation. Before coming to the general statement of Coulomb's law, let's see what is Coulomb's law actually in simple words. So, Coulomb's law is an experimental law. Experimental law means the Coulomb's law is determined experimentally. We can't derive it mathematically. Through experimental observations only the Coulomb's law was stated. That's why it's written like this: Coulomb's law is an experimental law. And that quantifies the amount of force between two stationary point charges. In simple words, the Coulomb's law enables us to calculate how much is the force acting between two stationary point charges. And this term, stationary or static point charges, is having some significance in Coulomb's law. The Coulomb's law is applicable to only static point charges. If the charges are in motion, we can't calculate the force acting between them using Coulomb's law. So we can treat this as one of the limitations of Coulomb's law. Coulomb's law is applicable only to static point charges or bodies having spherical symmetry. I hope you know the concept behind point charges, even though I will just point it out for you. What do you mean by point charges? For example, if I have two charged bodies A and B, separated by some distance smaller. Assume that A and B is having same radius. That is, both are having same size. And under this condition, that is, if the distance separating them is very much greater than the size of the charged bodies, we can treat A and B as point charges. So by definition, we can say like this: when the linear size of charged bodies are much smaller than the distance separating them, the size may be ignored and the charged bodies are treated as point charges. Clear? So the Coulomb's law helps us to calculate how much is the force acting between two static point charges. Now, the Coulomb's law was published in the year 1785. Before 1785, after conducting so many experiments on charged bodies, people knew some facts about electric charges. People knew that there are two types of electric charge in nature, and conventionally they are known as positive charge and negative charge. And people also knew that like charges repel each other and unlike charges attract each other. But people were unable to calculate the amount of force acting between these charges or charged bodies. For example, take this negative charge and this positive charge. These two charges will attract each other. Similarly, these two negative charges will repel each other. But people were unable to determine with how much force this negative charge is being attracted towards this positive charge. Similarly, with how much force this negative charge is being repelled by its neighboring negative charge. So people were unable to calculate the amount of force acting between charged bodies. So at that time, this man came, Charles Augustin de Coulomb. He was basically a French military engineer and physicist. He is best known for his discovery of Coulomb's law. He also did important work on friction and magnetism. The SI unit of electric charge, Coulomb. You learned in lower classes the unit of electric charge, and it was named in his honor in 1908. Okay, but how he calculated the force acting between two charged bodies? How did Coulomb arrive at his law from his experiments? Let's see. So for calculating the force acting between two charged bodies, Coulomb used the apparatus called torsion balance, and this is the apparatus torsion balance. So a torsion balance mainly consists of a cylindrical glass case which is closed with a metallic lid. A glass tube emerges from this metallic lid which is attached with a metal case, and this is known as torsion head. A torsion fiber is suspended from this torsion head and which holds a horizontal needle, and this horizontal needle is attached with a metal coated ball at one end and another balancing sphere at the other end. And also a circular scale is attached with the cylindrical case and from which we can note down the readings. Another static metallic sphere which is having identical size as that of the metal coated ball is placed at the 0 mark of the circular scale. The metal coated ball can be moved with the help of a micrometer attached with the torsion head. So that was a simple description about the torsion balance. But while performing all these experiments using torsion balance, Coulomb was unable to calculate how much is the charge accumulated on the metallic spheres. How then he could arrive at the relation of force? For that, he took a simple idea called conduction. You learned in previous classes the three methods of charging: conduction, friction, and induction. Conduction means we can make a neutral body charged one by bringing the neutral body in direct contact with a charged body. Through direct contact with a charged body, we can make a neutral body a charged one. This is known as a conduction. So Coulomb took this idea to carry out his experiments. As an example, take two metallic spheres A and B. Metallic sphere A is charged and it is having some amount of charge Q. Assume that it is positively charged. It is accumulated with some amount of positive charges. And the metallic sphere B is neutral. Assume that both are having same radius. Both are identical in size. Next, I am bringing this metallic sphere A and making in contact with the metallic sphere B. Now what will happen? The charges will get redistributed between these two metallic spheres. That is, the charge will be shared between these two metallic spheres. The charge from metallic sphere A will start to flow from this metallic sphere to the metallic sphere B until both are having same amount of charge. That is, after conduction, the charge accumulated on metallic sphere A will be equal to Q by 2 and charge accumulated on metallic sphere B will be equal to Q by 2. Exactly same amount of charge gets redistributed between these two metallic spheres. And this is because only they are having same size. If they are not identical in size, the charges from A will flow to B until both are having same potential. Okay, so Coulomb took this concept to carry out his experiments. Now let's see how he did his experiment using this concept and using torsion balance. We can call this metallic sphere as static metallic sphere and this one as rotating metallic sphere, because we can rotate this one with the help of micrometer screw attached with this torsion fiber. Okay. Now, initially, the static metallic sphere is given some amount of charge Q by bringing a charged object in contact with it. So, initial charge on the static metallic sphere is equal to Q and initial charge on the rotating metallic sphere is equal to 0. Now, the rotating metallic sphere is brought in contact with the static sphere using the micrometer screw. So what will happen now? As I told you, due to the property of a conduction and due to the property of a sharing of charges, charges will flow from the static metallic sphere to this rotating metallic sphere. And since both are having same size, the charges will flow from the sphere to the rotating metallic sphere until both are having same amount of charges. Okay, so after conduction, the charge on the static metallic sphere will be equal to Q by 2 and the charge on the rotating metallic sphere will be equal to Q by 2. And this is only because both are having same size. So after conduction, charge on static sphere will be equal to Q by 2 and charge on rotating sphere will also be equal to Q by 2. So now both are having same amount of positive charges within them. So what will happen? They will repel each other. And that amount of repulsion we can note down as deviation from the scale attached with the cylindrical glass case. The static sphere is now discharged by grounding it. And the rotating sphere, since it is attached with an insulating needle, the charge on the rotating sphere remains as Q by 2. So after discharge, the charge on the static sphere will be equal to 0 and the charge on the rotating sphere will be equal to Q by 2. Next, by adjusting the micrometer screw, the rotating sphere is made in contact with the static sphere. So what will happen now? Again, due to conduction, there will be sharing of charges between these two spheres. That is, Q by 2 amount of a charge from the rotating sphere gets shared between these two spheres. And since both are having same size, exactly same amount of charge will be distributed between these two spheres. So after conduction, the charge on the static sphere will be equal to Q by 4 and the charge on the rotating sphere will be equal to Q by 4. And again, the two spheres is having same amount of positive charge within them. So they will repel each other and the amount of deviation is noted from the circular scale attached with the cylindrical glass case. But the deviation was lesser than the previous case. In the first case, the charge accumulated on both the spheres were Q by 2. And at that time, they shown a large amount of deviation. But with the charge Q by 4 on each sphere, they shown less deviation. From this, we can conclude that the force of propulsion or attraction is directly proportional to the product of magnitude of the charges accumulated on both the interacting spheres. So from the experimental observations, Coulomb concluded that the magnitude of force acting between 2 point charges is directly proportional to the product of the magnitude of two charges. In more general way, we can say like this. If there are two charges Q1 and Q2 separated by some distance r, the magnitude of force acting between these two charges is directly proportional to the magnitude of the product of two charges Q1 and Q2. The magnitude of force is directly proportional to the magnitude of product of two charges Q1 and Q2. If the magnitude of a product of two interacting charges is more, the amount of force acting between the charges will be more. If this magnitude is less, small amount of force only will be acting between the charges. So, this was one conclusion Coulomb made from his experimental observations. Now, while doing the experiment, Coulomb noticed one thing. He observed that the deviation shown by the metallic spheres was varying with respect to the distance between the metallic spheres. So, to study that, he made the magnitude of charge accumulated on both the metallic spheres the same, and he varied the distance by adjusting the micrometer screw. And he observed how much is the deviation with r as the distance between the metallic spheres. And then he varied the distance using the micrometer, and he observed what is the deviation for distance r by 2 between the metallic spheres, and similarly he observed what is the deviation for distance r by 4 between the metallic spheres. So after all these experimental observations, Coulomb concluded that the magnitude of force acting between 2 point charges is inversely proportional to the square of the distance between the charges. Inversely proportional to the square of the distance between the charges. And we can represent this relation mathematically like this. For example, assume that we have two charges Q1 and Q2 separated by some distance r. The force acting between these two charges is inversely proportional to 1 by r square. Force and distance are inversely proportional. So, this is known as inverse square law relation. And you learned one more inverse square law relation in class 11, which is Newton's law of gravitation. The Newton's law of gravitation, F is equal to G m1 m2 divided by r square. So, according to Newton's law of gravitation, the force acting between two objects is directly proportional to 1 by r square. So, similar to Newton's law of gravitation, Coulomb's law is also having inverse square law nature. So, the Coulomb's law is also known as Coulomb's inverse square law. Now, from his all observations and from his conclusions, he stated his famous law, and this is the general statement of Coulomb's law. Coulomb's law states that the magnitude of force between 2 point charges is varied inversely as the square of the distance between the charges and is directly proportional to the product of the magnitude of the two charges and acted along the line joining the two charges. The sentence acted along the line joining the two charges means the electrostatic force acting between two static charges is acting along the line joining the two charges, and hence the electrostatic force is also known as a central force. Central force means the force which is acting between the centers of two interacting bodies. So the electrostatic force is also known as central force. Now we have to represent Coulomb's law mathematically. From the statement of Coulomb's law, we know that the magnitude of force acting between two static charges, is directly proportional to magnitude of product of charges and inversely proportional to r square. Magnitude of force is proportional to 1 by r square. And by combining these two relations, we can write F is proportional to Q1 Q2 divided by r square. So this is only a relation. We have to make this as an equation. And the relation we can make into an equation by removing the proportionality by introducing a constant. And we are introducing a constant k by removing the proportionality. So F is equal to k q1 q2 divided by r square. And this k is known as Coulomb constant or electrostatic force constant. Now the value of k, the Coulomb constant or electrostatic force constant, later found, and which is equal to 1 by 4 pi epsilon. So now we can rewrite the Coulomb's law like this. Magnitude of force is equal to 1 by 4 pi epsilon Q1 Q2 divided by R square. Instead of a Coulomb constant, we can write 1 by 4 pi epsilon. So this is the general mathematical representation of a Coulomb's law. Magnitude of force acting between two charges is equal to 1 by 4 pi epsilon into magnitude of product of charges divided by R square. Now you learned a new term epsilon. Epsilon is known as the electric permittivity of a medium. For the better understanding of this term, I am taking the example of refractive index. We learned refractive index in lower classes. Refractive index of a medium actually describes one property of that medium, which describes how fastly light can travel through that medium. Similarly, electric permittivity also describes one property of a given medium, which describes how easily electric field lines can pass through that given medium. Clear? Electric permittivity means, or electric permittivity describes how easily electric field lines can pass through a given medium. We can find the electric permittivity of a given medium using the expression epsilon is equal to epsilon 0 into epsilon r, where epsilon 0 is the electric permittivity of a free space or vacuum. Epsilon r is the electric permittivity, is the relative permittivity of the medium. Epsilon r is known as the relative permittivity of that medium. Epsilon r sometimes also known as the dielectric constant of a given medium. Clear? Electric permittivity of a given medium we can find using the expression epsilon equal to epsilon 0 into epsilon r. Now the value of epsilon 0 is calculated experimentally, and its value is equal to 8.854 into 10 raised to minus 12 Coulomb square Newton raised to minus 1 meter raised to minus 2. This is the value of electric permittivity in free space or vacuum. And from this relation, epsilon is equal to epsilon 0 into epsilon r, we can write an expression for relative permittivity. Relative permittivity epsilon r equal to epsilon by epsilon 0. So this epsilon r is just a dimensionless number. Epsilon r is a dimensionless number which is comparing the relative electric permittivity of one medium with respect to the free space or vacuum, just like refractive index. Refractive index n is equal to c by v, which is comparing the speed of light in vacuum with respect to speed of light in a given medium. Refractive index is also a dimensionless number. Thus relative permittivity is also a dimensionless number. Okay, and experimentally calculated dielectric constant of some materials I am listing here. The relative permittivity of a free space is 1 and the relative permittivity of air is 1.0006. That is, we can take the epsilon r value of air approximately equal to 1. And the dielectric constant of rubber is varying from 2 to 3.5. Dielectric constant or relative permittivity of paper is varying between 2 to 2.5, and for mica sheet it is varying from 3 to 7, likewise. So this is the relative permittivity of few materials. So now I am able to calculate the magnitude of force acting between two charges. Now I know the mathematical expression of Coulomb's law. The magnitude of force is equal to 1 divided by 4 pi epsilon Q1 Q2 divided by R square. So from this expression you can see here, along with these two factors Q1 and Q2 and R, the distance separating them, the property of a medium is also affecting the magnitude of force. So mainly three factors are affecting the force acting between two point charges. They are magnitude of interacting charges, distance between the charges, and the medium. The property of medium here is the electric permittivity. So in which medium the two interacting charges are present? Depending upon that, the value of F will change. For instance, assume that the two charges Q1 and Q2 are located in air. Then how we will calculate the magnitude of force? We have to find the value of epsilon of air first. And as I told you, to calculate the value of epsilon, we can use the relation epsilon equal to epsilon 0 into epsilon r. Value of epsilon 0 already find experimentally, which is equal to 8.85 4 into 10 raised to negative 12. And value of epsilon r also is found experimentally for each material, and from the table we can find the value of epsilon r. And just now we saw that the value of epsilon r of air is equal to 1, which is approximately equal to 1. Actually, the experimental value of epsilon r of air is 1.0006. So we can take the value of epsilon r approximately equal to 1. Now substituting the value of epsilon r here, you will get the electric permittivity of air is equal to epsilon 0 into 1. That is, in the case of air, instead of epsilon, you can simply substitute epsilon 0, since the value of epsilon r of air is 1. Now this equation we can rewrite like this. Magnitude of force is equal to 1 divided by 4 pi epsilon 0 Q1 Q2 by r square. Now you know the value of epsilon 0, the value of pi. Just substitute the values in the equation. Magnitude of F is equal to 1 divided by 4 into 3.14 into 8.854 into 10 raised to negative 12. And you will get F is equal to 9 into 10 raised to 9 Q1 Q2 divided by r square. So in a problem, if in the question they are specifying the two charges are located in air, calculate the value of magnitude of force acting between the charges. So in that question, if the medium is air, you can directly use this equation. 9 into 10 raised to 9 Q1 Q2 divided by r square. If the medium is air, then only. You know that the charge unit of electric charge is Coulomb. Now from this expression we can give a general definition for 1 Coulomb. For that, if I am taking Q1 is equal to Q2 is equal to 1 Coulomb and R is equal to 1 meter, then this equation will become 9 into 10 raised to 9 Newton. That is, instead of Q1, I am substituting 1 Coulomb. Instead of Q2, 1 Coulomb. And R is equal to 1 meter. So, this term will be equal to 1 and I will get F is equal to 9 into 10 raised to 9 Newton. From this, we can give a general definition for 1 Coulomb. Now, 1 Coulomb is the charge that when placed at a distance of 1 meter from another charge of the same magnitude in vacuum experiences an electrical force of repulsion of magnitude 9 into 10 raised to 9 Newton. That is, if I have two charges Q1 and Q2, they are separated by a distance of 1 meter. And if experimentally I am finding what is the force acting between them, and if I am getting the force acting as 9 into 10 raised to 9 Newton, I can say that the charge accumulated on Q1 and Q2 will be equal to 1 Coulomb. Clear? If the charge accumulated on two interacting charges separated by 1 meter will be equal to 1 Coulomb if they are experiencing a force of 9 into 10 raised to 9 between them. Okay. And this Coulomb is a bigger unit. So, while doing problems and all, sometimes we will take the smaller units like 1 millicoulomb, microcoulomb and nanocoulomb. 1 millicoulomb is equal to 10 raised to minus 3 Coulomb. And microcoulomb 10 raised to minus 6 Coulomb and nanocoulomb 10 raised to minus 9 Coulomb. And in coulombs, I told you how to calculate the value of epsilon. Epsilon equal to epsilon 0 epsilon r. So, if the two charges were present in air, instead of epsilon, we can write simply epsilon 0 because the value of epsilon r is equal to 1. So this is the equation if the charges were present in air. Now, apart from air, if the charges were present in any other medium, how we will write the expression for force? Simply, instead of epsilon, we have to substitute epsilon 0, epsilon r, q1, q2 by r square. This is the expression if the charges were present in any other medium apart from air. And already we calculated the value of 1 by 4 pi epsilon 0, and we got that value as 9 into 10 raised to 9 Newton. Sorry, 9 into 10 raised to 9. So the equation can be written as F is equal to 9 into 10 raised to 9 divided by epsilon r q1 q2 by r square. Instead of 1 by 4 pi epsilon 0, we can write 9 into 10 raised to 9. So while doing problems and all, if the two charges were present in any other medium apart from air, you can use this relation. Epsilon r of mediums will be provided while doing problems. So you need to simply substitute instead of epsilon r the value of the particular medium. Now we can do a comparison between magnitude of force in air with the magnitude of force in any other medium. If I am taking F as the force in air acting between two charges, and F dash is the force acting between two charges when the charges were present in any other medium. And I can write expressions for F and F dash. Here equation number 1 represent the magnitude of force if the two charges Q1 and Q2 were present in air, and if the two charges were present in any other medium, the expression will be F dash is equal to 1 by 4 pi epsilon 0 epsilon r q1 q2 by r square. Now I am dividing equation number 2 with equation number 1. I will get F dash by F is equal to 1 by r, because here I am changing the medium only. The rest of all the parameters remains the same. Q1 magnitude of charges I am not changing, the distance between the charges also not changing. So all the terms will get cancelled out, and I will get F dash by F is equal to 1 by epsilon r, or I can write F dash is equal to F by epsilon r. That is, the force in any other medium is equal to 1 by epsilon r times the force in air. Now this is an important formula. This you can use while doing simple problems. So mainly three factors are affecting the force acting between two point charges. They are magnitude of interacting charges, distance between the charges, and the medium. When the magnitude of interacting charges increases, the force will increase. When the distance between the charges increases, the force will decrease. And in the case of medium, the magnitude of force is actually proportional to 1 by 4 pi epsilon. 1 by epsilon. And the value of epsilon is least if the medium is air or vacuum. So apart from air or vacuum, if we are keeping the charges in any other medium, the force will decrease. So these are the three factors which affect the magnitude of force acting between two static point charges. Now so far we discussed about how to calculate the magnitude of force acting between two charged bodies. If I have two charged bodies Q1 and Q2 separated by some distance r, now using Coulomb's law, now I can calculate with how much force this Q1 is being repelled by Q2, and with how much force this Q2 is being repelled by Q1. But we know the force that we are dealing with is a vector quantity. So along with how much force, we have to specify in which direction that force is acting. We have to specify the direction of action of a force also. So next we are going to see how to represent Coulomb's law in vector form. Now, to represent Coulomb's law in vector form, along with the magnitude of force, we need to just add the direction of force. That's it. And now let's see how to add a direction along with the magnitude of force. I'm taking here example of two point charges Q1 and Q2. Here I'm taking two positive charges. Q1 and Q2 are two positive charges. You can see few vectors are represented in this diagram. Let's see each vector one by one. I told you, here I am taking the example of two positive charges. Q1 and Q2 are positive charges. So you know, like charges will repel each other. So Q1 Q1 will be repelled by Q2 and Q2 will be repelled by Q1. So this will be the direction of force experienced by Q1 because Q2 is repelling Q1. Similarly, this will be the direction of force experienced by Q2 because Q1 is repelling Q2. Okay, so here this vector F12 represents the force on Q1 due to Q2. The force experienced by Q1 on Q2, we are using the vector representation F12 to denote that. Similarly, F21 is the force on Q2 due to Q1. Clear? F12 is the force on Q1 due to Q2. F21 is the force on Q2 due to Q1. Now, assume that I am observing these two charges from this point. So, I am taking this as the origin and R1 and R2 are the position vectors from Q1 and Q2 respectively from the origin. R1 is the position vector from the origin to the charge Q1. R2 is the position vector from the origin to the charge Q2. Okay. Now another vector R12. Vector R12 is the position vector leading from 2 to 1. That is the position vector acting in this direction. Position vector leading from 2 to 1 is represented as R12 and R12 we can write as R1, vector R1 minus vector R2. Similarly, the position vector leading from 1 to 2. The position vector from 1 to 2 is represented as R21. Position vector leading from 1 to 2 is represented as R21. And similar to this, we can write R21 is equal to R2 minus R1. So, by comparing these two equations are only a difference in sign. So, we can write R21 is equal to minus of R12. Okay. So, these are the vectors presented in this diagram. We have F12 force and F21 force. F12 is the force experienced by Q1 due to Q2. F21 is the force experienced by 2 due to Q1. Similarly, R21 is the position vector leading from 1 to 2. R12 is the position vector leading from 2 to 1. So, I told you vector R12 represents the position vector leading from 2 to 1. The properties of vectors you learned in class 11. If I have a particle which is traveling with a speed of 10 meter per second along y direction, I can represent its velocity like this. Velocity is equal to 10 j cap, where 10 represents the speed or magnitude of velocity of that particle and j represents in which direction the particle is moving, which is moving along y direction. So similarly, all vectors we can represent in this format. A vector we can represent along with its magnitude and direction. So vector R12 also we can represent like this. Vector R12 is equal to magnitude of R12 and the direction. For representing the direction of a position vector, we are using unit vectors. Okay. So, you learned about unit vectors in class 11. So, here R12 represents the unit vector leading from 2 to 1. The position vector, the unit vector pointing from 2 to 1. Similarly, I can represent R21. Vector R21 is equal to magnitude of R21 into unit vector R21. So, this R21 represents the direction of vector R21. This is the direction pointing from 1 to 2. Okay. And this also you learned from this. By rearranging the equation, you will get an expression for the unit vector r cap 21 equal to r21 vector r21 divided by r2, magnitude of r21, and r cap 12 is equal to vector r12 divided by magnitude of r12. So now we can represent the force experienced by charges in their vector format. Okay, I took this example, the interaction between two positive charges. I have two positive charges Q1 and Q2, both are repelling each other. Now I am going to write the expression for force experienced by Q1 and force experienced by Q2 in vector form. So the force experienced by Q2, that we are representing using the vector F21, where F21 represents force experienced by the second particle, that is Q2 due to Q1, and which is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square. And this is the magnitude of force experienced by Q2. This is written with the help of Coulomb's law. Next, to represent the force in vector form, we need to add its direction also. In which direction F21 is acting? F21 is the force experienced by Q2. Q2 is experiencing force along this direction. This is repelled by Q1. Okay. So to represent the force along this direction, we have to take the position vector acting along this direction. And the position vector acting along this direction is r cap 21. R cap 21 is the position vector, unit vector acting from 1 to 2. The position vector acting from 1 to 2 is r cap 21. So the direction of F21 is along r cap 21. Similarly, the force experienced by Q1 I can write like this. F12. F12 is the force experienced by Q1 due to Q2 is equal to, again the magnitude is same, 1 by 4 pi epsilon 0 Q1 Q2 by R square. Next we have to add the direction. Q1 is also gets repelled by Q2. So this is the direction of force experienced by Q1. So we have to add the unit vector acting along this direction. The unit vector acting along this direction is r cap 12. R cap 12 is the position vector leading from 2 to 1. Position vector leading from 2 to 1. So F12 is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square r cap 12. Now we can write r cap 12, just the difference between r cap 2, unit vector r cap 21 and r cap 12, just they are acting in opposite direction. So I can write r cap 21 as the minus of r cap 12 or r cap 12 as the minus of r cap 21. So I can just modify this equation like this. F12 is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square. In this equation, instead of R cap 12, I can write minus of R cap 21. Okay. Now, what is the difference between these two equations? Equation of F21 and F12, only the difference in is negative sign. So I can write F12 equal to minus F21. F12 is the force experienced by Q1 and F21 is the force experienced by Q2. So from this we can conclude one point, that the Coulomb's law agrees with the Newton's third law. So the same thing we can do for unlike charges also. Instead of two positive charges, here I am taking one positive charge and negative charge. We can represent them in vector form. Okay. So here is Q1 and this is Q2. This is positively charged. This is negatively charged. And we know that the unlike charges will attract each other. So here this is the direction of force experienced by Q1 due to Q2. That is, Q2 will be attracting Q1 towards it. Similarly, this is the direction of force experienced by Q2. Q1 will attract Q2 towards it. Okay. And F12 is the force experienced by 1 due to 2. F21 is the force experienced by 2 due to 1. Now, how will represent in vector form? F12 is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square. And we have to add the direction along with the magnitude. In which direction F12 is acting? F12 is the force experienced by Q1 which is acting along this direction. Which is the vector? Unit vector acting along in this direction. The unit vector acting along in this direction is r cap 21. So here we have to write r cap 21. Next, the force experienced by Q2. Force experienced by Q2 is equal to F21 is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square. And the direction of force. The force experienced by Q2 is acting along in this direction. And which is the unit vector acting along in this direction? The unit vector r cap 12. R cap 12 is the position vector, or a unit vector leading from 2 to 1. Position vector leading from 2 to 1. And F21 is acting along that direction. So, we can write F21 is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square R cap 1. So, likewise, we can represent the force experienced by charged bodies or charged particle using Coulomb's law. So, now let's revise the important points that I discussed in this video. In this video, I discussed about Coulomb's law and its vector representation. In simple words, Coulomb's law helps us to calculate the force acting between static point charges, and that force acting between static point charges depends upon three factors: the magnitude of the interacting charges, the distance between the charges, and the medium in which the charges are present. And mathematically, we can represent the force equation as magnitude of force is equal to 1 by 4 pi epsilon Q1 Q2 by R square. This magnitude means while calculating the magnitude of force if the interacting charges are unlike charges. For example, if Q1 is positive and Q2 is negative, no need to consider the negative sign of Q2. That's why we are writing magnitude of Q1 and Q2. Okay, divided by R square. And this, what is this epsilon? Epsilon is the electric permittivity of a medium, and that we can calculate using the equation epsilon 0 epsilon r, where epsilon 0 is the electric permittivity of a free space or vacuum. Epsilon r is the relative permittivity of the medium, and if the charges are present in air, we can write instead of epsilon 0, because for air the value of epsilon r is approximately equal to 1. And we can calculate the value of 1 by 4 pi epsilon 0, which will be equal to 9 into 10 raised to 9 Newton. So we can write this equation as F equal to 9 into 10 raised to 9 Q1 Q2 by R square also. Then we discussed how to represent the Coulomb's law in vector form. We can represent the Coulomb's law in vector form by adding along with the magnitude the direction. We are specifying with the help of position vector. So these are the important things that we discussed in this video. Children, after watching this video, read NCERT textbook. In this video, I covered topic 1.6 from the NCERT textbook.